So when you have a partial differential equation, here's the heat equation shown again. It's a second order partial differential equation in three-dimensional space, and it requires, it has a time component to it as well. So the question is, how many boundary conditions or initial conditions do we need to solve a problem like this? Because we need boundary or initial conditions to solve differential equations and partial differential equations. So this is the equation again, assuming isotropic properties. Let's start with the boundary conditions. Let's look at the boundary conditions for this equation. So, well, before I go there, let me ask a question. How many, for this general form of the equation, how many boundary conditions do we need? Well, it's second order in each spatial coordinate. So we need two, right? So we need two for each spatial coordinate. So that would be a total of 6 boundary conditions we would need for this problem. What about initial conditions? Well, it's first order in time, so we only need 1 initial condition in this case. So we're going to start with the boundary conditions. We're going to go over boundary conditions, and we have a Dirichlet boundary condition, which basically is a constant surface temperature. This is saying that we have this surface that we fix it at a temperature. A real-life example of this would be a boiling fluid or a melting solid, something going through phase change, because when it goes through phase change, it stays at the same temperature. So that could be a constant temperature boundary condition. Shows up a lot in practice. Basically, that looks like this mathematically, that at position x equals 0 on the surface, and for any time, we have a fixed temperature T sub s. And I should note here, so we're now moving to the boundaries of our problem. When we derived our heat equation, we said that the energy in and energy out, those rate balances would only include Fourier's law, the conduction rate equation. And that the convective equation, Newton's law of cooling, or Stefan Boltzmann's law for radiative heat rate, that they would happen on the surface. So we're going to see how that shows up as we move along to some of these other boundary conditions. So now we have a constant surface heat flux. So this is saying, this is different. Here we had a temperature that was fixed on the surface. Now we have a set heat flux. So you can have an electrical heater that's attached to the surface. You can have some sort of device that's giving off a known amount of heat, known heat flux, like a computer chip. And that would be the boundary on the problem, that heat flux. So here we'd have minus x, partial derivative of t at x equals 0 for any time, equals this constant heat rate. So here it's heat flux. So Q double prime sub S is heat flux watts per meter squared. And then we have this other case where it's the same. It's a Neumann condition, constant surface heat flux. Except in this case, the heat flux equals 0. So this is an insulated boundary condition. This is a boundary where no heat can transport across that boundary. So one of the things I want you to note in this course is how the temperature profile changes at these boundaries. So here for constant surface temperature, basically you have this fixed point that the temperature profile has to converge to. Where for a constant surface heat flux, and we'll see this more later, because at the surface here, we're balancing Fourier's law to determine the heat flux. There's a constant slope that this line has to come to. So the temperature profile has to come to this slope here that satisfies the boundary where Fourier's law is applied. And that slope is important. We're going to have to learn to draw these slopes throughout the course. One salient example is when we have an insulated boundary condition. Notice here that the slope flattens and loses all of its steepness. So we end up with a flat line. And basically that's indicating that this surface is insulated and that the temperature profile goes to zero. The temperature gradient goes to zero at that boundary. Because you can't have a temperature gradient if there's no heat flow. And you can't have heat flow if there's no temperature gradient. So when we have an insulated condition at the wall, the slope of the temperature profile goes to zero. So I'm going slow through this just to make sure that these points have time to set in. The last condition we have is the convective surface condition. And it's called the convective surface condition, but this could also be radiation as well. But basically this is a mixed boundary condition. And by mixed, what that means is that here we're equating at the boundary the conduction leaving the boundary or entering the boundary with Fourier's law. We're equating that to what's happening at the boundary, and in this case it's convection. We have H, the heat transfer coefficient, times the difference in the ambient temperature and the temperature at that boundary. So this is the third type of boundary condition we can have. Here balancing Fourier's law and Newton's law of cooling, and it also could balance Fourier's law and Stefan Boltzmann's law, and in this case everything is kind of mixed together. So we didn't go over initial conditions, but you probably think, okay, if we had a situation where at one of these walls, let's say that at time zero, it is held at this constant temperature Ts, but after time zero, that temperature of the wall could change. For example, you can mix that with a heat flux boundary condition. If you apply some heat flux to a wall that's at room temperature, you know that temperature is going to change with time. But the initial condition is that it's at room temperature at that point on the wall. So the question I have for you now is, you do solve these problems using math. And there's certain boundary conditions that constrain a problem and are necessary in order to get a solution that's meaningful. So you can imagine that for a problem, let's say that we, for each of these boundary conditions, had some, well, let's simplify the problem. Let's say we're dealing with one-dimensional conduction. Partial derivative of temperature with respect to x, the second order, and no generation, and we had some transient effects we can leave in the energy storage. So the point is that if we, on one side of a wall where we have one-dimensional conduction, fix a temperature, and we fix the temperature on the other side of the wall, we can solve the problem. We can solve for what the temperature distribution in that wall would be. But what if we had two heat flux boundary conditions, two boundary conditions of the second kind satisfying that problem? So I want you to think about that. Let's imagine if you just had a slab, and on one side of the slab you fix it with there's cool water at a given temperature, keeping that surface temperature constant, and on the other side there's something heating it up. You can imagine that you can figure out what the temperature distribution is using the heat equation, and it's going to have some set known value. Anywhere in this slab, the temperature is going to be in between temperature 1 on this side and temperature 2 on this side. But if you had the same slab and you put some sort of heat input on this side and a different heat input on this side, or if you insulated it on this side so there was no heat input and the heat flux was zero, and you put another heat input on this side,